Hello everyone, I hope you had a nice weekend. Here in Tarragona it's Santa Tecla time, so there are a lot of parties. So Mariam, if you see us sleeping today at one moment, like then you can understand why. No, I'm joking. I think we are all in a good shape. Yes. So let's start. Today is the last theoretical lecture of this crash course. And as I was mentioning before, like to the guys here, even though like the hands-on lecture is very heavy, we will not go that deep in theory because there are a lot of concepts that you don't need. So I'd rather prefer you to focus on the things that you need rather than to lose 1 hour understanding spin spin orbital coupling. That is something that you will never use in your life because if, in case you need to learn, then you will learn it later. There is no need to spend your brain now to learn something that you don't need now. So, yeah, as we say, today we start with the correction of exercise 3, and then we move to answer 4. Answer 4, you will just have 3 exercises. Usually in the answer 4 from VASP, we have like 6, but I removed 3 of them because I don't think it's something that you should spend time on. So, but you will get all the information, so don't worry. As always, all the material on OneDrive. Also, this lecture is already on the OneDrive and some folder, so you can find it. And yeah, as I said, we start with the correction of exercises of Anson 3. Then we move to lecture 4 and instruction for Anson 4. I merged actually these 4 lectures in one single presentation that I also uploaded. So this is just basically like a presentation made of some slides for each of these 4. So you can just have a look on this one. If you are curious and you really want to learn everything, then go ahead and check all the 4. But a lot of things are not really important. Like for instance, like this DFT depth, it's really like going again on all the things that we did on the first lecture. So again, saying, okay, we need to solve the Com-Sham equations, and then you have the exchange contribution that you can solve in different ways. So if you really want to go through that, there are a lot of formulas, go ahead, but it's not that needed at this stage, okay? So don't worry about that. And then like the answer section is the number 4, again is uploaded. But the important and relevant exercise that you need to do is already inside this VASP summary. So if you just check this VASP summary presentation, it is the one that I will go through today. You have everything you need, okay? Then we go to the answer 3 question, okay? These were very general questions, so I guess you should have an answer. We will see if any of you has the answer, and then I will give you my answer, okay? So the first question was like, define the surface energy. So more than define, let's say calculate surface energy for nickel 100, nickel 111 based on the formula that you see there. Define which is the most stable crystalline facet, compare with experimental values, and then based on a paper that I put in the last presentation, you also needed to tell me which one of the two you think is the most abundant on a nanoparticle. Okay, so let's start value of the surface energies. Did you calculate them?
Yes. Yeah.
How much?
I have for the 100 a value of 0.33 and for the 111 0.19.
Okay, 0.19. Okay, good. So, which is the most stable between the two?
The second one.
So nickel 111. Did we compare with experimental values? Did we find any experimental values?
I did it, but not in the article that you put it.
No, I mean, in the article that I put, there was no. Okay. In the article that I put was the last point. Which facet is the most abundant? Okay. So how much is the experimental value for nickel?
And the nickel 111 is which?
No, I mean, now I'm asking about the experimental value for the surface energy of nickel. Okay, so that is the value. Does any of you have it?
No.
Doesn't matter, I have it. So here you see how I calculated, that is your same way. You see that in my case I approximated, but it's still like in line with what Enrique said. Don't worry if the value is slightly different because there are a lot of different parameters, so no problem. The important point that you should focus on is the trend. So all of us got that nickel 111 has a lower surface energy than nickel 100. because nickel 111 is more stable than nickel 100. Okay, then if you multiply this value that you got in electron volt over angstrom square by 16.02, then you can convert your surface energy gamma into the surface energy given in joule over square meters. Okay, and this is the value that is usually given experimentally. Okay, so you see that I did that and I get values that are around like 3 joule per square meter for nickel 111 and 5.6 joule per square meter of nickel 100. And you see that if we compare to other state-of-the-art DFT value or two experimental values that are here, you see that actually we are kind of far away, because this is 3, and for 111 we got 2, and for 100 is 2.4, and instead we got 5.6. Okay, so we are happy because we reproduce the trend in the sense that we could see actually the 111 is the lowest energy, but you see that like the absolute value is really far away from state-of-the-art DFT and experimental value. And what is the reason for that? The reason for that is simply because our setup is not optimized. I mean, like, if you don't optimize your setup, then you get the trend that is correct, hopefully, but your absolute value will be wrong. So, like, the take-home message here is just like the answers are just for you to know how to calculate surface energy, but they are not optimized with the nice key points, energy cutoff, and everything, so that you can get exactly the value that you should get. Because actually, if you optimize it, like key point mesh, energy cutoff, you should get value closer to this one. Okay, and here you have the reference where I got this value. Okay, so if you go to this reference, you get this value. Third point, which facet is the most abundant on a nickel nanoparticle? Any of you have had a look on the last on the paper I mentioned?
I just had a quick look, but not find it.
Okay.
It's 111, I think.
Yeah, but why is 111?
Because it's more stable.
Yeah, okay, this is a good explanation, but let's say like there is a theorem that explains that, and the theorem actually I can just go quickly on the paper, so you can see where like I mentioned it. So now soon I'm going to share it. Just want to go directly to the section. Okay, where is it? Here. Not here. Really? Yes, this one. Okay. So this is the paper that I shared with you in the last time, and at one point you see this section. This section is talking about the Wolff theorem. Okay, this Wolff theorem, developed in 1901, states that the lower the surface energy of a facet, the largest contribution it has in the equilibrium structure of a given material. So if we want to translate that in current English, that means that lower the surface energy, more abundant that facet will be on a structure, so in this case a nanoparticle. Okay, and why I had this question for all you? Because in case some experimentalists ask you, okay, look, you need to model some nickel nanoparticles. The way you do, you calculate the surface energy of nickel. You see that nickel 111 is the lowest energy configuration, and then you can use just this facet in your model, and you explain that, say, look, experimentally they have nanoparticles. If they have XRD characterization, then it's perfect, because you can directly say, look, they see experimentally 111, 100, so I model 111, 100. But in case you don't have XRD, then the way is instead to say, look, I calculate 111 is the lowest energy configuration according to the Wolff theorem. That means that is like the facet that is the most abundant, and so you just say, look, this is the value. Okay, so just for you to remember that part, because you may have to apply that in your future, like according to the project video. Okay, then let's move to the next question. How much is CO absorption energy on nickel 111 compared with experimental values? So, did you calculate?
Yes.
Okay. Sichen, you also calculated.
Yeah, manner
Okay, because I mean, Enrique already answered what?
0.29.
Uh-huh.
30. 30.
Minus or plus?
Minus.
Okay, so what does it mean to have a negative?
Negative means it is how that expands energy is more stable.
Exactly. So that means that if the binding, well, if the absorption energy is negative, means that your surface is binding the adsorbate. Okay? So if it's positive, means that like your adsorbate doesn't want to be on the surface, but it's negative, means that like the energy of your overall system is more stable than the energy of the clean surface plus the molecule when they don't have any interaction. So the fact that this difference is negative means that like the molecule is happy to be on the surface. Okay, did we have any comparison with experimental values?
I found one which is near, that is 0.31, but after that I have seen that the coverage is not the real one, because this is with a 0.2 coverage value.
Okay.
So,
okay.
As I understood the last session of doubts, with a higher coverage, it must be greater. A greater number in a positive number.
Exactly. Yes.
If we
Should increase, like, should be less negative, let's say.
Yes. Should be less stable with a higher coverage. Okay.
Okay. I also like look for some number. You will see that some of them are a bit different than the one on the rig, but because it's really depending on experimental value.
Yes.
Okay, so don't worry about that. As you Chen said, minus 0.3 makes sense. These are all the three energies. So basically, just did this, minus this, and you get minus 0.3. There is no mysterious things here. And in this paper, they calculate like the rate of absorption, and the heat of absorption is basically like the opposite of the absorption energy. Okay, because what they calculate here with the rate of absorption is how much heat like a molecule need to be dissolved. So it's the opposite process than the one that we are here mentioning. So you see that the value are given in kilojoule per mole. Qi is at initial low coverage, and Qf is final steady state coverage. So this is like with higher like surface coverage, let's say, and you see that the value that I get for nickel 111, 100, 110, these are experimental values, are minus 1.4 electron volt in low coverage and minus 1.0 in the steady state, so higher coverage. Okay, so you see that this is what we were discussing now with Enrique, that if we increase the coverage, then this value gets less negative, because means that like it's easier to dissolve the molecule. Okay, but you see that there is still a great difference, at least in this case with the experimental value, between like this minus 1.0 to minus 0.3. And the reason for that is because at the steady state, even though like we will have a higher coverage, we will never have a coverage of 1 that we are here. Because for sure there will be a repulsion, so the CO will just escape. Okay, so that's the reason why they get minus 1.0 and they get minus 0.3, because we are modeling here a coverage that is not physical, that will not happen physically. So we are getting a number that it's okay, can give us an idea that whenever you have a lot of CO, there will be a lot of repulsion. But if you calculate, for instance, CO absorption energy and you put this number, that is wrong. In the sense that like you are telling something that is not true in the experimental system, because you will never get to one monolayer. Okay, that is just again like to kind of like highlight what we were discussing with you and the last time, that surface coverage, whenever you talk about absorption, is very fundamental. Okay, because depending on the surface coverage, you see like here the energy is changing by 0.4 electron volt, and that's a lot. Okay, so that's just to remember, whenever like you need to calculate something, try to understand what is the coverage, or you calculate different coverages theoretically, and you say, look, at this low coverage I have this value, medium coverage is value, high coverage is value. So at least you have an idea or how much is the mistake or the uncertainty. Okay, then yeah, why does DFT underestimate the experimental value? We just said it. I forgot to let it go before. Last things, list nickel carbon monoxide vibrational frequencies and compare with experimental values. Did you get the frequencies?
Yes.
Okay, how much?
The frequency between the carbon and the oxygen was 2139, and the surface with the carbon it's 415.
Okay, yeah. So these are the two values that Henrik just said, exactly. And as for the experimental value, like I found this paper that is actually a DFT paper. Okay, so these values are DFT calculated, and the only experimental value is this one. Okay, so you see, like the way that VASP give you the frequencies, they even give you like directly the frequency, so the wave number, centimeters to the power of -1, but they also give you the energy. Okay, so like in this case, you can compare directly the energy, and you see like the calculation that we have is in line with the calculation of like previous like state of the art DFT. Well, not really state of the art because this is really old, but one of the DFT calculation, let's say. And what is nice is that you see that since we are doing this calculation 40 years later, more or less, than they do, we get like better agreement with experimental value in the sense that like we get like an energy for like the nickel CO stretch that is like around 51 milli electron volt. They got 49.7 and experimental one is 59. So we get a bit closer. We are still far away, but we get a bit closer. And the reason why we don't mimic one by one experimental value is simply because whenever you have vibrational frequencies, there are some systematic mistakes with DFT. So again, like DFT is very valuable and really strong in getting to the trend, but they fail a bit whenever they want to give you the absolute value. Okay. So again, this is just to tell you that you should be always extra careful when you try to compare one by one experimental value with DFT value, because in DFT we have some systematic mistakes. Okay. Yeah, and I think we are ready. So now we can go, oops, not here, but we can go to the big presentation that I just mentioned. So, okay, better put it here so I'm getting a bit faster. So, scores. Yeah. So, as I mentioned, this is a big merging with just the important things. So, and feel free to stop me at any time you want, okay? So the first thing that we will discuss today is about the accuracy, okay? So we already discussed the other time how the accuracy is related to the key point like mesh. Today we will discuss a bit more about like the energy cutoff, okay? So yeah, the overview is like the plane wave energy cutoff, that say higher we have, more accuracy we have, also longer the time for the simulation. We will discuss a bit like some parameters, not all of them. I mean, I will not go through the PREC parameter because actually I never touch it in all my 3+1 years at ICQ. So I don't think you have to touch it either. And then like related issues in case. So the energy cutoff, we already said like in the very first lecture, then this is just controlling like the threshold where we are stopping the kinetic energy of the electrons. Okay, so when we apply the Bloch theorem, like we can take the potential as a periodic function that makes it, then we can express the wave function also as a periodic function of like the periodicity of your system. And here the cutoff is just telling you when you want to stop checking, let's say, like all the different like energy levels for your kinetic energy of the electrons. Okay, so more like, let's say, higher energy cutoff you get, more accurate your simulation is. However, the problem is that then also the simulation will get longer because you will need to, let's say, calculate over like higher number of plane waves. Okay, so the important point that you need to remember is just that the cutoff rules the accuracy together with the key point mesh. And usually the energy cutoff that is given by n cut are given in the podcast. We will see it later how you can retrieve it from the podcast. Anyway, the important like number is that whenever you set a value for the energy cutoff, it's usually around, well, usually we set it to 450, okay, 450 electron volt. And then if you're doing some very, very special electronic properties calculations, or you are optimizing a bulb, you can increase it by 30%. Usually I put it to 600 electron volt, but still the standard value is 450. Okay, so n cut in Incar is the parameter you put in Incar and should be equal to 450 electron volt. Of course, electron volt you don't put because like the Incar doesn't need to have the unit of measure. Then here, yeah, it's just telling you like some internal corrections that let's say that VASP is doing, and also that due to this correction the energy might increase, whatever, like it's not that important. Let's say this would be the value without this internal correction by VASP. This in red is the value of your mistakes, let's say, given when VASP correct. But the only important point that you need to focus in this graph is that at one point, after a certain value of the energy cutoff, you see that your mistake goes to zero, your error goes to zero. So that is the important point, because there is no difference to stop and or to put a threshold that is here rather than to put a threshold that is here. The only difference will be that if you put the energy cutoff here, then your simulation will take maybe double the times. Instead, if you took here, if you stop here, you are optimizing your system in the best way, so that you take the best compromise between having the best accuracy you can get, but also the good time. Okay? Then, yes. Then the question is like, okay, I just told you that usually we are putting 450 as the energy for the cutoff. And then the question is like, is it a good value always? And the point is like, not really, in the sense that this is good always whenever you keep the cell shape and the volume fixed. You calculate vibrational frequency because it's frozen phonon calculation vibrational frequencies, surface and slab calculation, adsorption of molecules. Okay? So which of these points is not covered? The point that is not covered is bulk optimization with easy 2 or 3. So with the parameter that let you modify the cell shape. Okay, so if you remember, whenever we were optimizing the bulk, the way to optimize it automatically is to let VASP decide which is the best cell shape and volume. Okay, so like to change the lattice vector so that you can have a bulk that is like, that has a larger like lattice vector or smaller. Okay, and in case you do such a simulation, then you need to change the energy cutoff because you can have a mistake. Okay, and this increase already is usually is around 30%. Okay, so it's 450 electron volt plus 30%. As I said, usually I put 600. Okay, so only for bulk optimization you need to touch the energy cutoff. Otherwise, for other things, usually this 450 is okay. Yeah, then yeah, yeah, here there is nothing again that special to say. It's just telling you that like, what is the problem? Okay, the problem is that like you need like that the energy of your system varies also with the volumes. Okay, so that's the reason why you also need to kind of adapt your energy cutoff whenever you're changing the volumes, because otherwise the problem is that you will be simulating two different things. Okay, and you can see it, for instance, here. You see, because here this calculation is the one done at 240 electron volt, and this one is the one at 270 electron volt energy cutoff, and you see that 270 is lower in energy. So here, that's the reason why you need to use, for instance, 270, because then you get that the energy is better. Okay, and then you see that also the other important parameters are the key point density, because you see that here in the red one that you put 2 per 2 per 2, so you have a very, very, very few key points. You see that the energy gets completely like well, fail completely. You don't have much convergence, because you see that here you have basically a step function, and here, like, you don't really get to the minimum like here, like you have something more discontinuous. So again, like, remember that you need to optimize the energy cutoff and the key points together. So what I just said means that, for instance, let's say if you have problem with the convergence, doesn't make any sense that you increase the cutoff to 800 electron volt and you keep a key point mesh of 2 per 2 per 2. Whenever you want to increase, you need to touch both properties at the same time. So you increase a bit the cutoff, but you also need to increase the key point density, because otherwise, as we said the other time, these two properties are connected, because like the key points mesh gives you more or less an idea of the discretization in the Brillouin zone that you take in order to calculate the wave function for the electrons, and the cutoff tell you when to stop. So if you have really bad discretization, so that means really, really few key points, I mean, it doesn't matter how accurate you go to every single point, because you still have very, very few points, and vice versa. So remember to work with both parameters at the same time. Yeah, like, usually whenever you do this optimization of this bulk optimization, you also use this E star equal to 2. And now we are going to check what does it mean, this E star equal to 2 on VASP. So now that when the internet will get ready, kind of slow today. Very slow, actually. Wow. Okay, no, I think this is okay. We will skip it. So yeah, the only important point about this E star 2 is that what you do with E star 2, you just like calculate, you retrieve the basis set from your wave card. Okay, so you need to have like a previous calculation where you calculate the wave card, and then you retrieve like all the electronic density from the wave card. That is the most important part that you should remember. Okay, but again, like, don't worry too much about that, because usually you get all these parameters again explained in the info. Okay, so it's not something that you need to learn by heart now. Yeah, here is just telling you what we just said. You know that the problem is that if, let's say, like, well, how can you say, let just to visualize what we just said. Okay, so whenever you put, so given this as the Brillouin zone, let's say, the idea of the energy cutoff is like that you are covering like part of it. Okay, okay, yeah. So what is the problem? The problem is that if you increase the cell volumes, at the same point, what you do, you also reduce your Brillouin zone. Okay, because like longer the lattice vector, smaller the reciprocal lattice vector. And so, like, since you reduce that, you also reduce, like, accordingly, like, let's say the same value of energy cutoff will cover like a smaller, will cover the same percentage of the Brillouin zone, but still, like, in absolute value, you see that the area covered here, this one, is lower than this one. So this is the problem, that if you change the lattice vector, even though you are keeping the same energy cutoff, let's say the absolute, let's give it like the absolute, like, threshold will change, because the Brillouin zone is changing for both of them. Okay, so yeah, just telling you that, like, yeah, at larger volumes the energy is overestimated, and yeah, for fixed basis set is underestimated. But again, like, don't focus too much on what is happening. Just remember that whenever you change the volume, so you do a bulk optimization, then you need to be extra careful and increase the energy cutoff. Okay, yeah, and this is, yeah, exactly. Okay, this is telling you, like, the stress tensor is something that you calculate, for instance, when you do a bulk optimization, And so what it's telling you here is what I just told you, that whenever you do bulk optimization, you need to increase the cutoff by 20, 30%. Okay? And you see here why, because this value is completely wrong. Okay? This is like the pressure calculated at the equilibrium lattice parameter of FCC copper. So this value is completely wrong because the cutoff energy is completely wrong. And instead the good value is this one, okay? Because here you get to a like few kilobar that is like also corrected with experimental value. Remember that the one that we use is 450, so the one that we use is here. So we don't have any problem. I mean, you don't need, like, you would need to think about all these things only if you use the energy cutoff that is exactly given by the podcast file, but usually to avoid any mistake, we put 450, and 450 usually works for all the systems that are important for us, like transition metal. So you will not need to think too much. Just when you do a bulk optimization, you might need to use 600 electron volt instead of 450. Yeah, this is just what telling you, so that if you do a cell shape relaxation, increase the cutoff by 30%. And if you want instead to have a quick and dirty calculation, yeah, like you can then correct by mistakes, but I mean, like, never do the second point, just increase the cutoff by 30%. So put 600 electron volt and then we are happy about that. Okay? Yeah, and the very, 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 very last thing, and this is our the common mistake. Remember, and that's the reason why, for instance, in the last answer, when you were supposed to calculate the absorption energy for CO, they also made you repeat the DFT energy of your surface, because you cannot compare surfaces if you have a different energy cutoff, because that's completely wrong. And you cannot compare energies if you have different key point mesh. So just remember that whenever you want to calculate absorption energy, surface energies, whatever, you always need to keep the same energy cutoff. And for instance, that's the reason why we got so bad value for the surface energy of nickel. Why? Because the energy cutoff that we use for calculating the surfaces was different than the energy cutoff that we use in the bulk. Okay, so if we have different energy cutoff, we still get the right trend, because let's say we do a systematic mistakes, we do the same mistakes for nickel 111 and nickel 100, but the absolute values are wrong because we are comparing like apples and pears. I mean, two different things that we cannot compare. Okay, so just remember to use always same energy cutoff. That's why we always use like this 450 electron volt, and to use the same key points. And that's the reason why for the key points you are doing the script now, that we just tell you, look, whenever you have something, you need to have key point mesh, so that you have like reciprocal grid size of 0.03, like angstrom to the power of -1. That means that, let's say, if you have like lattice vector of 6 angstrom, then you need to have 5 key points in that direction, okay, for the monster.
Sorry, when you talk about increasing by a 30%,
yeah,
in the cases of the shape relaxations, you were talking a 30% from the 450. Okay.
but usually we just put 600. That is much more than 30%, but we put 600. Okay, well, I mean, no, actually it's not more, right? Because 450, 10%,
1/3.
yeah, so it's
Yeah,
okay.
more
Yeah,
or
so 450, 600, that means like increase by 30%.
yes.
Okay. Yes, and this is just telling you to validate result. So if you see problem, if you don't get proper like comparison with experimental value, increase the cutoff, try to perform these precision accurate calculations. I never did it, so usually the cutoff is good enough. And if still doesn't work, increase the number of key points, increase the slab thickness, and increase the size of the superstar. Okay, so what does it mean, these 2 points? Okay, these 3 points, and then I think that now I will just make a very, very small like drawing in there. So like as we mentioned the other time, okay, so periodic boundary condition, this is a cell, really badly done. You have, for instance, like 4 layers, and here is the vacuum. Okay, so this is the vacuum. I will put just B to mention that this is the vacuum. And remember that since it's periodic boundary condition, that means that also here there is the very same cell. So when it's telling you increase the slab thickness, means that you need to increase the vacuum. Because, for instance, let's say if you have really poor vacuum, so let's assume that you have like 2 angstrom of vacuum, okay? Like this. This is just 2 angstrom. So this system is completely wrong. Why is wrong? Because like this layer will feel attraction or repulsion from this layer. And this cannot be. Because in reality, these 2 layers don't see each other. Because, I mean, we just use periodic boundary condition to save time. But periodic boundary condition should be done in such a way that there is enough difference so that the 2 facets, the 2 periodic facets don't see each other, okay? So this is the first point. And then for defects, increase the size of the supercell to remove artificial interaction. These artificial interactions are, for instance, the CO-CO repulsion that we just saw, okay? Because when we mention like increase the size of the supercells, means that now we are checking our slide in the top view, okay? So if we are checking it from the top view, means that, for instance, if we have like, let's say that every cross is a CO molecule, okay? In this case, it's like one monolayer coverage. I mean, this is not a physical like system. So you multiply the cell, for instance, by 4. So now you have something like that. And then either you keep this 4 to equal, or like you remove this one, okay? And then this would mean that then you have just this one here, this one here, this one here. So now you don't have any more like artificial repulsion between the 2 CO that cannot be there, but you have the repulsion that is expected in a normal like atomic system, experimental systems, okay? So just remember like number of key points to be increased, increase the slab thickness, that means that you make it like your like slab just longer, well higher, you increase the Z direction, and size of the supercells, you increase X and Y direction.
But sorry, could you repeat again that concept of artificial interaction, please?
Yes. So artificial interaction means okay. Let's put it another way. Okay. Now think that like this is the top view, and okay, yeah. Now I have it. So now let's assume that you want to check how easy is to have a copper atom. Okay. So here we have a copper atom, and we want to check how thermodynamically it's easy to have a copper atom here. Okay. Of course, like the thermodynamics of this copper atom is completely different if we are checking a periodic like system that is like that, or a periodic system that is like this. Because if we check a periodic system that is like this, then here we have another one. Here we have another one. Here we have another one. But here we have an artificial interactions. I mean, and what do you mean by artificial? Like artificial, like it's not that is intrinsically wrong. It's just that it's an interaction that you will not see in your like experimental system, because in the experimental system you have a big surface, and it will never happen that if you start like a nucleation process, it starts like within 5 angstrom. Okay, so like you need to adapt the size of the supercell so that you have a proper like distance between one event, let's say, and its periodic image. So in this case, for instance, you have maybe a size here that is like 8 angstrom, and that is good enough, because at 8 angstrom, well, this is a really bad 8, but still, at 8 angstrom, like this and this will not feel that much repulsion, okay? So there will not be repulsion. It means that like whatever is happening here will not affect this one, and that is what you want to achieve, okay? Because unless you are considering high coverage simulations, normally you are assuming that there is no interaction between one image and its periodic condition.
But for example, in a surface, you have that interaction. So the surface is periodical.
Yes, I mean, So you have, but depending on the size of your supercell, you can lower it. Okay? In the sense that if you're using a big cell, a big enough, like 8 angstrom, it's okay. You can assume that like you can try actually, but you can assume you have such a low coverage already that if you use this cell or you use a cell that is even larger, the delta E absorption of CO will not change anymore. And why it doesn't change anymore? Because you reach a distance that is good enough so that you have screening. So that any local like effect that this CO has on the surface is already like decaying after this 8 angstrom. So like for the new CO here, there is no difference. To have, I mean, this CO is not able anymore to fill the other CO, okay? And usually it's what we want to have on a surface. Because usually all the catalytic like effect are happening in this condition because you have a big, like you need to think that like usually you take like an electrode, for instance, in electrochemistry, that is something like one at least square millimeters. And I mean, and here we are talking about angstrom. So 10 to the power of minus 10 meters. So we are really, really in a small scale. So like, it's really unphysical to think that, you know, like as you absorb and also the other one absorb for some of the reasons. If we want to study, for instance, CO coupling, of course, then you need to put them closer. But this is just to stress the point. Look, check your system and then considering if it makes sense to have a small supercells or a big supercell.
Yeah. I have a question.
Yeah,
because there, I mean, the CO that because the CO are 2 atoms and the 8 angstrom, the distance between the 2 form means that from the carbon 8 and the oxygen to another oxygen.
Exactly. Yes.
Okay.
Yeah, because you need to now if we go to the side view, so let's say this is our surface. That means that we have a CO here, and then the next CO will be within the periodicity, so the next CO will be here. Okay? So depending on the size of the supercell, this distance can be 8 angstrom, can be 10 angstrom, can be 100 angstroms, or can be 2 angstrom. And the game here is to find a value that usually 8 angstrom is okay, so that, let's say, the repulsion between them is already goes to 0. You need to think, let's say, if this is a graph of repulsion versus like distance, of course, like there is a threshold values where your repulsion goes to 0. And usually this one is 8 to 10. That is already good enough. If you want to have the best simulation ever, you can also like just have a supercell of 100 angstrom, and then you for sure will not have any interaction, but will also take months to convert. So the reason why you adapt it is just because you want to have the smaller supercell ever, because smaller the supercell, lower the number of atoms, faster your simulation, but you want still to have a large enough supercell so that you don't have artificial interaction.
And this year I have think about it in the last weekend about that. I mean, in the here we have just a small molecule.
Yeah.
And if we have a bigger one, and how could I? There is some condition for it. Just for example, if there is a small molecule with 2 atoms, we should set the distance with this. And if we have
I understand. Of course, I mean, this is a parameter that you need to consider because, like what you just said, that if now we have something different, okay? I mean, now I'm really making up a really bad molecule, okay? But just to give an idea. Of course, if you have something like this, then 8 angstrom shouldn't be calculated between this carbon and this carbon because, like, the real distance is this one.
Yeah.
So basically, you just need to check your systems and to make sure that you still have enough space between one big molecules and the other one. I mean, it's not that like this 8 or 5 angstrom, like don't take it as like a must of like, okay, we need to check 8 angstrom. You just need to make sure that like your molecule, whatever size it has, is in a position so that it can have enough distance from its periodic image. Okay? And so that means that if you have a bigger molecule, yeah, then probably you will need to have a larger supercell, okay? But usually, like you decide before, you optimize before the size of the supercell so that it's good for all the molecules, okay? Because for sure, what you cannot do is to take like a supercell like this for CO and to take a supercell like this for instance, ethylene, just because it's large. Because remember, if you change the supercells, you change the coverage as well, because the number of atoms are always the same. Okay? So like usually what you do, you optimize your supercell large enough so that it's good for all the large molecule, and also you calculate the small molecule here, no problem. Okay?
Okay.
Good. Then I think now I need to close this annotate move. Okay, now we go to the pseudo potentials in the functional. Okay, so we are changing completely the page. Okay, this is another lecture. So this is the lecture two pseudo potentials. Okay, but as I said, I merged the two. So if you already, I mean, I don't know if, I think we already put them inside of the answer, but if we didn't, then we will put it when you do the real DFT simulation. We are using PBE, okay? And we are using the GGA like approximation for calculating the functional. And in order to tell VASP what we want to do, like in the inker, you add a line where you put GGA equal to PE, and you put PE because we are using the PBE functional, okay? So all this big slide is to say that in your case, you will always, well, not always, because you may also want to use other functional, but let's say in the standard DFT you are applying, you will almost always use GGA equal to PE because we're using the PBE functional, okay? At least in my life, I always use the PBE function in 4 years of SAT. Then, after having, let's say, discussed, remind all of you that we are using the PBE, then now we need to talk about the pseudo potentials, okay? Because now you get the pseudo potential done. I mean, the podcast file was already given, always, but you will need to generate yourself and you will need to decide which one you want, okay? So in order to get this pseudo potential, now I will just show you where you get it in case now the connection is getting better. Okay, so yeah, now it seems that it's getting a bit better. So usually where we get all these, now let's zoom it a bit. Okay, so usually we in the group we get the pseudo potential like, okay, now I forgot that I need to do this comment. Okay, no, it's okay because I'm already. So we got it from from the boss, from Nuria. So like, it's not that all of us needs to have a local copy of the pseudo potential. Okay, like we simply have like a general like folder in like the Tekla home of Nuria, and so we always like take the value from here. So you see like PPS, then we use the pseudo potential from VASP 5.4. I mean, you will use, now we are using 5.3, but I mean, in the future we use 5.4, that is the last version of VASP. And then we use the pseudo potential for the PBE functional, so we enter PBE. And you see that we have different version. We take the last one, so POTPO PBE 5.4. So what you get here is a list of all the possible pseudo potential. Okay, so if you open, for instance, C, okay, it's a directory, yes, because in C then you have podcast, okay. So now if we open podcast, this is simply the podcast for a carbon atom. So let's say whenever you were using the podcast for the C and O, for the carbon monoxide, for instance, then what it means is that you were just concatenating this podcast for the carbon with the podcast for the oxygen, okay? And usually, at least in my case, I have a script to do that, and also all of you in the future, you will have a script. So in my case, I have a script that is actually pot. So this is a script that is taking the coordinate from the postcard and then is just generating the postcard, applying another script that is called podgen. And if I go to podgen, what podgen is doing is just entering like the directory where we have the repository of the pseudopotential. In my case, I have it locally on my Tekla home, simply because like when I started, I decided to copy, but I mean, that is not the policy in the group anymore. So we just copy it from the Tekla home of Nuria directly. And then what this script is doing is just to take the podcast from the repository. Okay, so it's just saying, okay, look, you have in the system a carbon and oxygen. Then in your case, we'll go to the folder of Nuria and we say, okay, print the podcast of the carbon and append to this podcast the oxygen, because there is also the oxygen. And here you have a message, error message that is telling you, look, you don't have element in your postcard, so I cannot generate a postcard, because if you don't tell me which elements are in the system, I cannot generate. Okay, but again, don't like this one, you will get the two script when you need to start running simulation. In your case, like for all these and so on, you already noticed that you always got the postcard done. Okay, so as we mentioned, we use the PBE potential. You have used the PBE for all the answers, and the PBE pseudopotential, all the information are included in the podcast. Okay, so just to go very quickly, when we just did more podcast. So when we open the podcast looks like that. Okay, it's telling you, okay, how it was calculated, the day. So you see that these are kind of old. Then the number of electrons. So in this case, this is aluminum. So two like electrons in the s orbital, one electron in the p orbital. Remember that these are the valence electrons, because what the pseudo potential does, give you an approximation for the inner shell electrons and just explicitly consider the valence electrons. So in this case, just three, and then a bunch of other important like information. And here you have nmax. So this is the value that is relevant, because if you need to touch the NCAT, you need to make sure that the NCAT value is always much larger than the NMAX. So as I said, usually we use 450, and this is good enough because you see that the NMAX here is 240. But still, if the system fails, you may have a look, and maybe for that special exotic element, the NMAX was 500. So if the NMAX is 500, then you need to use a NCAT in your INCAT that is 600, 700, because it needs to be higher than the NMAX. Okay, this is the minimum NCAT you can use, but usually you want to go higher to have better accuracy. So this is, you can open yourself a podcast file. The first line looks exactly as this. Okay, of course, like the parameters are different. So in case you have carbon, you will like here C, and then you have the different like electrons, and then all the other information. Okay, nothing special. I mean, you don't need to learn them because they are in the podcast, so no reason for you to learn this. Yeah, and then here is explaining what I just told you. Second line, the valency, the atomic configuration, then the energy cutoff, absolute lower limit for energy cutoff, required energy cutoff. Still, 450 electron volts and you're done. Okay, and here you see, and probably you have seen also before when I opened the folder of Nuria, that like apart from like B or C, you see also some like subindex. And you're like, but why you have this? I mean, why you have three pseudo potentials for carbon, for instance? I mean, like you should just have one, right? Because as I mentioned, like the pseudo potential works assuming that they consider just some electrons, but depending on the accuracy that you require, you may also want to increase the number of electrons in the valence shell. So whenever you see something different, is because you have a different number of electrons considered in the valence shell, so you can get better accuracy in your simulation. So yeah, you see, like for instance, potential that are called like nickel V, let's say, introduce also like well, the d electrons as a valence, I mean, the case of nickel is a bad example because in the case of nickel, d are already valence electrons. But let's say if you are in a case where you shouldn't, yeah, like germanium, for instance, where you can also not, or gallium, where you can also avoid to consider the d electron when you have this d, well, or indium, because on indium, let's say the valence is mainly p and s, but you may also want to consider the d, because maybe you need to go to higher accuracy. So this pseudo potential will have in this line additional electrons, accounting also for the electrons in the d orbital, okay? And yeah, like X hard is for very small core radii, and also like, so this one is just for very, very specific simulation, but I mean, don't worry because I never use it again. This is just to get like a very, very big like overview. Okay, then like depending on like yeah, like in this case you can use this like as if there are no bonds between first row elements, but I mean, for carbon I always use the standard carbon, never use this carbon S. So just remember these slides, because in case Nuria one day or somebody will tell you, look, try to change the pseudo potential, you can come back to this slide and say, look, let's check, okay, this, okay, I need a hard pseudo potential, so let's go for the BH. I need a soft pseudo potential, let's go for the BS, okay? But you don't need to learn it now because there is no reason. Usually you will use the standard one. Okay, yeah, this is just telling you the difference, for instance, in bond length. You see that depending on like using a hard like pseudo potential of the standard one, you can get some difference. And you see that there are really, really, really minor differences, okay? But for some simulation may be relevant to have this difference. I mean, maybe the hard is working better than the standard one, okay? Okay, here is telling you, is again like telling you the standard one. Remember that the red one are the standard. So red means that you will usually use the red one, okay? So that's why in my case I always use the red. And also like a lot of system I never used. Like for instance, like never like studied gallium, germanium, never happened. Okay, so like for that you will use mainly transition metals and organic molecules, and in that case they are the standard one without any sub-index. Here is just a big again overview about like the things. Is also like telling you, look, remember to make tests, because whenever you use a new pseudo potential, you need to check that you have the right energy cutoff. So remember to go through that. Remember that depending on the number of electrons in the valence shell, then you have, let's say, if you have 10 electrons, then you will have 20 bands, because you need to have a band for each each spin of the electrons, okay? Well, sorry, the opposite. If you have 10 electrons, then you need to have 5 bands, because you can have like 2 electrons for each band, okay? So if you take 20 electrons, you will also need to increase the number of bands on your system, or your system will get longer to simulate, okay? So like, that's the reason why you always want to use the pseudo potential that optimize and minimize the number of electrons in the valence shell, because more electrons you have in the valence shell, longer your simulation will be. More accurate, but also longer. So you need to get like a compromise between the two things, okay? Then, this is mainly for cation, so I actually needed like to fight with that for one project, in the sense that like, so in this case, for instance, just means like, yeah, like let's say the standard value for sodium, for instance, is just taking like the s orbital, and if you want to use this one, is also taking the p orbital from the inner shell, okay, and so on. So for and for lithium, basically you also take the 2 orbital that you have in the inner shell, in the first inner shell, okay? But again, like this is just if you're working on cation, so you probably never work with that, don't worry. Just remember that you can access and consult this slide if you need to change the pseudo potential. And then, yeah, you see like for XPV, so sodium PV, for instance, pseudo potential, the semi-core P states are treated as valence, so 2p in sodium, 3p in potassium, etc. For XSB, So lithium has VIPs with potential. The semi-core states are treated as valence. So in case of lithium, also like the 2 electrons in the first s orbital. Okay, and then the very last things. Okay, yeah, this is just like about, yeah, like to remind you that like what is the definition of the pseudo potential. That like you use the pseudo potential just to have a soft approximation of the wave function within a certain like radius that is the kind of cutoff radius. So that means that here you have the proper calculation of the valence electrons, but from here to here you have an approximation. So you are just assuming, okay, the inner electrons have a certain effect and I am approximating a certain effect like that. While this line is the line that you will achieve if you assume that all the electrons of your system are valence electrons, but will also take a lot of stuff because you will have a lot of electrons in your system. Okay, and you see that for the transition method, the one that you will probably use, you see that the most common one are the standard ones. So copper, nickel, palladium, platinum, iron, nothing strange. Zinc, cadmium, like silver, gold, manganese. You see that like there are also other pseudo potential, but you will not use them. So that's the reason why I'm telling you, don't worry too much if at the end of this class you say, okay, but I don't remember properly what is H subindex. Doesn't matter. I mean, in case you need to check the H subindex, you will enter this slide or go online on the VASP manual and understand it and remember it. Okay, doesn't make sense for you to focus on that now. Yeah, and if you have again all the explanation, yeah, this is not very important. Okay, yeah, and this is just telling you, and I mean, and I put it because that was important to me for one case, that in case you want again to study cation, like, and usually all these cation are really challenging because you also have the F electrons, and we will see later why F electrons, well, F orbitals electrons are problematic, but in case you want to avoid something, you need just to check them as cations. So without some of the electrons, there are also some pseudo potential that are this one, and these are the pseudo potentials for these elements as cations. So these are these elements minus 3 electrons, okay? Because these systems can also very easily lose 3 electrons, so you have like cerium 3 plus, neodymium 3 plus, and so on. But again, guys, don't like just remember that there are different pseudo potential depending on the number of valence electrons you want. Okay, and now we go to the very last big theoretical things of today before going quickly on the answer. So on-site Coulomb repulsion. So here we will very quickly introduce why for some systems, namely the systems that have strongly correlated D and F electrons, so D and F, well, electrons in a D and F orbital, you may need to like include an additional formalism that is called the Hubbard correction. Okay, you see a lot of formula here, but the only thing that I think is important for you to get is that what is happening is that if you remember, like when we split or when we apply like the first reduction approach on the Schrödinger equation, what is happening is that we are trying to solve this equation for each different electron. And so we have a term that include the interaction between one single electrons and all the other electrons. Okay? But now, let's, for instance, and if we want to make just a stupid example, okay, let's assume that the 4 of us in this room are all the electrons. So how we are solving the Schrödinger equation is like, I need to take the interaction with me and all the 4 of us. But that means that I'm also taking the interaction between me and me. And that is just an artificial thing from the reduction approach that we assume. Because I mean, an electron cannot interact with itself. Because the electrons, I mean, if the electron is in a position, the same electron will not be there. They are the same things, okay? And the problem with that is that if we have the D and F orbital electrons, they are very localized. So these self-interaction mistakes, these mistakes that happen because we are again, like consider interaction between an electron and itself will be much, much, much stronger for these electrons. So for systems that have D and F electrons, for instance, like any kind of oxide, because in the oxide, for instance, copper oxide, you have the electrons. If you have nickel oxide, you can also have again the electrons. Okay, so in that case, you need or neodymium or cereal. So in this case, you need to apply a correction on top of that, on top of the standard DFT. And so, yeah, here is just telling you that like you solve, let's say, all the equations, but what is important is this formula, okay? So the way that we solve it is by including a correction that is called the U-bar correction, so that we are correcting the energy of the electrons by two parameters that we optimize, U and G, okay? So let's say, that means that in the INCAR, you need to add like a bunch of lines where you say, look, for this system, since you have the localized electrons, you need to put the U equal to something, J equal to something. And to make it more clear, okay, so this is the formula, okay? This is the formula, but you don't need to put all this formula. What is important for you to know is that you just need to provide in the INCAR a value from the U, a value from the G, that you either optimize comparing your DFT value with experimental value, or you retrieve from previous state-of-the-art DFT results, okay? So, just making an example that will make everything easier, okay? Let's take, and actually pay attention on that because one of the answers, the last one, the 4.3 is about this. So this is the nickel oxide, okay? This is an insulator. So we say the other time that what does it mean that a system is an insulator? Do you remember? So if a system is an insulator, what is happening?
That the band gap it's higher.
Exactly. The band gap is very, very wide, very broad. Okay, so the difference between the valence band and the conduction band, it's a lot. So basically, the electron cannot easily go to the conduction band. Okay, and so if we are calculating that with DFT, we like in order to have a DFT calculation that makes sense, we should get to a very high band gap. Because if we get a band gap of 0.5 electron volt, means that our DFT is wrong, fails. And in case you want to study this system just with the standard DFT, so the one that we have done so far, you see that you get a band gap of 0.4. So this is wrong. It means that your DFT fails in accounting properly for the electronic properties of your system. And that is fully wrong. It's not that you can say, yeah, but I know that, because we know that we have these self-interaction mistakes. Yeah, there is these self-interaction errors. But since you are getting bad electronic properties, means that every calculation that you get here is wrong. You cannot get any experimental insight, any insight that you can then later provide to experimental. So what do? You apply this Dudarev approach. You will see in the INCAR what does it mean, this Dudarev approach. It means that you have one line when you put U is equal to 8, J is equal to 0.95 in this case, and now you see that you get a much better band gap, because now you see that you have a band gap of 3.38, and the experimental one is between 4 and 4.3. And you also see that the magnetic moment of nickel moved from 1.15 to 1.71, and the experimental one is 1.70. So how, like, when do you decide to apply the Dudarev approach? If you start with this system, you say, look, these are some d electrons, I need to be extra careful, because d electrons and f electrons are problematics. And then after you say, okay, yes, d or f electrons, let's see. Then you try like in a very naive way. So you don't put any U-bar correction and you say, okay, let's see if I can mimic properly the electronic properties. And then if you see, for instance, that you get a band gap that is like 1/6 of the value that you get, then a bell should ring in your brain and be like, oh, look, here I need to apply the Dudarev approach. Because otherwise, I am mimicking things that are not physical. And then you apply the Dudarev approach. And how do you apply the Dudarev approach? The J, you usually keep it equal to 1. Here is 0.95, but usually you keep it equal to 1. And you start tuning the U. So you start with a U equal to 1, U equal to 2, U equal to 3, U equal to 4, U equal to 5, 6, 7, 8, 9, 10, 11, 12, whatever you want. You do all these tests. And for instance, here you can map the band gap versus the U that you are inserting. And you will reach an optimal value because you will reach the value that is, let's say, making your DFT calculation to reproduce experimental result in the best way ever. And that will be the U that you decide. So this U equal to 8 that they took, they simply took because they calculate the band gap. They say, okay, 338. Oh, this is close enough to the experimental one. Oh, this U is good. Okay. But the way to get the U is always having some benchmark with experimental system, because the problem is that DFT alone fails. Okay. Okay, and then we can quickly go to the Anson. As I say, the Anson of today are really for dummies.
Sorry,
Because,
is
yeah.
there any words or some or handbook to tell us how to get the U? I mean,
The only way that you can get, and maybe I can annotate because then we get easier. So there are two ways to get it.
I remember from some article have said the U values will always be I mean the incorrect, I mean the unbelievable sometimes because there's a
I mean, so yeah, exactly. So the problem with the U in general, as you just said, is that the U is a artificial parameter. So the U is not a physical correction. Okay, so of course, like whatever U you put is, I mean, it's not wrong, but it's just a correction to DFT. But again, like also DFT is a model. I mean, DFT is not real. I mean, it's not real in the sense it's not physically real because you're making a lot of approximation. So the two ways to get the U, the first one is simply to look for, okay, and then I can put it larger. Look for other DFT studies.
Yeah,
this is the first because other people would have it optimized for you. And then in case there are not, then you look for benchmark with experimental studies. Okay? So benchmark means that if you have, let's say, if you are, nice, that is cancelling everything. So if you are, for instance, let's say a band gap, you can take band gap, magnetic moment, formation energies. So all these experimental like properties, so you take them from experimental studies and you calculate the same quantities with different U correction, okay? And remember that like you tune it, so 1, 2, 3, 4, if you want 5.5, I mean, it shouldn't be an integer, okay? You can also change it. And usually J instead is equal to 1. You keep it equal to 1, okay? And then here, if you do that, okay, now it's 1 over the other. If you do that, you will get, for instance, like, and now, yeah, I will do it here. You can get a graph, let's say, where you have, okay, because now it's, yeah, you can get a graph where you have, let's say, like the U as a X, and you can have, let's see, the B as a band gap here, and you will get something like that probably. Okay, maybe a linear correlation. And then you see if your experimental band gap is here, then you get to the U that you want to use, that is this one. So if the U here is 8, means that you need to use a U of 8, and the J, so this will be a U, while the J will be 1. But remember, you always first look for other DFT studies, if they already calculate, and if they don't, then you go to check if you can calculate, if you can tune the U and reproduce some strong experimental stuff. Okay?
If all of them cannot, right?
Eh?
If there are not reference values.
If there are not state-of-the-art values, then you go to experimental studies, yes.
Yeah.
And you check and you try to compare your DFT simulation with experimental values, and then you stop. But be aware that this is something that you should always do with DFT. I mean, whenever you model something with DFT, you always need to check that what you're simulating agrees with experimental values. Because if it doesn't agree, then it doesn't make sense to simulate, because you are simulating something that is not real. Okay? Good. Okay, so I think that now we can quickly go to the answer. So, okay, yes. Yeah, like, don't check this. So these three things, soy, constraining, what to, like these 3 points are not to do, okay?
Magnetic correlation.
I mean, the magnetic, you are doing it in the first point already, but like this spin orbital coupling, no. Don't waste your time here because it's very complex. We don't have like on our supercomputer VASP that is compiled to calculate that, and you will never use it. So it doesn't make sense for you to lose time on that. Instead, you will calculate FCC, nickel. So here you will apply the magnetic moment, and you will see that you need to reproduce that nickel is ferromagnetic. Then you will calculate nickel oxide, and you will see how the nickel oxide gets better. Well, the calculation gets more physical when you apply this Duderev approach, okay? So, very quickly, nickel, you get everything already done, okay? You have like your lattice vectors, you have your positions, and what you will have in the incar, that you see it here, it's the important part is that you're applying spin, so you have E spin equal to 2. You are putting the magnetic moment. The magnetic moment is 1. What does it mean to have 1 as a magnetic moment? Since here we have no, okay. Why? Okay, yeah. So the magnetic moment of 1 is simply because you have just 1 atom, okay?
Sorry, the minor means?
Huh?
The first here have the minor 10.93 and
Okay. Here, this is the lattice vector.
and the negative.
No, sorry, no. I'm confused. Yeah, this is usually the lattice vector when it's positive. When it's negative, is the volume. It's written here. Volume set to 10.93.
Oh.
So in the postcard, I mean, so the point is that remember, this is an FCC. So if you define the lattice vector of the volume is the same thing, because the volume you calculate as lattice vector to the power of 3. So these are the same things. The only difference is that, of course, they want you to put the minus just to tell the computer, look, I'm not giving you the lattice vector, but I'm giving you the volume. Because if you don't put the minus, then the computer will take it as a lattice vector because you're not able to understand it, okay? So, yeah, like, but don't worry much about that because usually we put lattice vector. It's just because, again, since they are hands-on, they want you to see everything. So now they're telling you, look, you see, like if you put the minus in front, this is the volume. But usually we always put the lattice vector because they are equivalent, okay? It's just because they want to be fancy now. So they want to tell you, look, if you have the minus, then it works. So, okay, here you have like the different like impact in your incar. So it is mere, if you remember, that means that we are using the tetrahedron method, okay? Magnetic moment is 1 because we have 1 atom of nickel. So like when you put this mag mom, means that you are giving the initial guess from the magnetic moment, okay? So 1 means that you are giving initial guess of 1. The unit, I think, is in, I think it's like, now I don't remember, but like, if you go to the VASP manual, they tell you which unit is this magma, but anyway, it's 1, okay? And then L orbit is, yeah, to get orbital resolved DOS. So if you remember, whenever we put L orbit equal to 11, then we are able, for instance, to see like all the different density of state given the system, given the element. And this VASP curve, yeah, the interpolation of the correlation part of the, yeah, this parameter we never use. So you can just check it in VASP for curiosity, but I never use it in my life. Okay. And I did calculation on nickel, like a lot of them, and I never use this. So, okay. Then, yeah, this is just telling you that in Oxycar, since you apply the spin, then you will get a magnetic moment. And you can also see the magnetization in the outcar. So, for instance, if you write, if you open like the outcar with more space outcar, then you have the outcar in front of you, and then you put slash magnetization enter, then you will get to this table. Okay, this table is just giving you the magnetization of your ions. You just have a nickel, so one split by the different orbital. So you see that the, let's say the total is 0.58, because you have minus 0.07 on the S, minus 0.026 on the P, and 0.625 on the D. Okay? So you can check the magnetic moment. Why? Because, okay, now yes. Okay, here it's telling you that you have the exchange splitting, not that important. Okay, yeah. Yes. Here is making you an example. If you want, you can repeat that in case you start with the same system as before, so this one, but instead of using magmon equal to 1.0, so the initial gas of 1, you put an initial gas of 0, then you will not get magnetization. Okay, so all this point is just to tell you, look, whenever you have a magnetic moment, since you want to be sure that you are properly going to the right physical state, then you need to have the nice initial gas. If you make a wrong initial gas, like magnetic moment equal to 0 for nickel, that means that your system will not be magnetic, then you see that actually VASP is telling you, yeah, don't worry, the system is magnetic, but you get here the energy is minus 0.54 to the power of 1, and here the energy is minus 0.5459. So the energy here with the magnetic moment is slightly more negative than the one without the magnetic moment, because nickel is magnetic. So it makes sense.
So that makes better if we give it larger value.
I mean, no, like it's not always better if you put a larger values. It's always better that you put the magnetic moment as the initial gas closer to the experimental magnetic moment for this element. So nickel, the value is 0.56, so you give 1. If you wanted to be even better, you could have put, instead of 1, you could have put 0.6. And this would have converged even better, because the experimental one and the one that you get with VASP is 0.57. What you cannot do is to put 0, because 0 is very far away from 0.6. So what you need to do is to put the magnetic moment that is the closest as possible to the experimental value. Okay? Because then your system will just converge to the right physical and electronic structures, not to a state that is not physical. That will be an artifact again. So now, after having said that, then we go to the nickel oxide. That is what we already mentioned before. So the nickel oxide, yeah, like rock style structures, antiferromagnetic ordering. Here you have lattice vector. Here you see that is positive because you have the lattice vectors. You have 4 atoms because you have 2 nickel and 2 oxygen. You have the 4 positions of these 4 atoms. You are using the Moncourt-Spack grid 444, because the lateral dimensional like 4 per 4 is like 30. Well, no, sorry, I'm getting from 16. Is a bit smaller, but still, like, again, the answers are not optimized, so it's okay. And what you do here, you see Then since this system is a bit problematic, so you apply spin, you have a magnetic moment that now is like 2 minus 2, 2.0. You will see that this is a different way than before. So before we just have 1.0 and that was all. Here we have 2, minus 2, and 2 per 0. What does it mean? With the magnetic moment, whenever the magnetic moments are different for each atom, then you need to explicitly put them. So this is the magnetic moment, the initial guess for the magnetic moment for nickel 1 atom. Minus 2 is the initial guess for the magnetic moment for nickel 2 atom, and oxygen don't have any magnetic moment, so 2 atoms of oxygen per 0 magnetic moment, okay? If you want, you could have put 0.0, 0.0, was the same. What you cannot put is 4 per 2, because if you put 4 per 2 means that you are assuming that all the 4 atoms that you have in the system have a magnetic moment of 2. And instead, in this case, since it's antiferromagnetic, you want to have plus 2 magnetic moment in one of the nickel, minus 2 magnetic moment in the other nickel, and 0 magnetic moment on the 2 oxygen. Okay? Then, energy cutoff, energy difference, really bad, like threshold, you should go lower, but again, it's just to, like for you to play with this value, tetrahedron method again, all these, that is a bit like puzzling, because like, okay, we never use this, why we're using it? You're using this because this system is problematic, as I said, it's antiferromagnetic. So these parameters are simply to do some linear mixing in the initial guess on the magnetic moment so that you will get to the convergence faster. So having this value or not having this value doesn't change like the accuracy of your system, of your calculation, sorry, but they do change the speed for convergence. So if you don't have them, it can take a lot of time and maybe also fail to converge. But if you play with this parameter, they will go faster to the last stage. Okay? So it just
Here in the considering the maximum part, could I put just 2 and multiply to minus 2?
yeah, but the point is that if you put 2 multiplied by minus 2,
yeah,
then you are saying that both your nickel atoms have a magnetic moment of minus 2, and that is not true, because it's antiferromagnetic. So you need to have one nickel atom plus 2, the other nickel atom minus 2. So that's why you cannot. Okay? Remember that, like, whenever you have a product, the first number is the number of atoms, and the second number is the magnetic moment. Okay? Good. So, done this, you will do this calculation. That is like the 4.2, and yeah, and you see the problem. Okay? Total magnetic moment 0. I mean, that is not too problematic because it's antiferromagnetic, so that makes sense. So you would be okay, but still, like, your nickel should have some magnetization. And then if you get the magnetization of the nickel, we get to the problem that we said before, that we get 1.21 instead of 1.70, that is the experimental one. But the big problem is the band gap. So the band gap is 0.44 instead of 4. So here, since the nickel has the orbitals and they are localized, then you will do the last simulation of this Anson. These are 3 simulations, very quick to do, using the Dudarev approach. Okay? For doing the Dudarev approach, you just need to add in the inker this line. So L dow true is just telling VASP, look, I want to do a Dudarev calculation. Please enable me to do that. You do. Then L dow type equal to 2 is just to, well, actually, sorry, like L dow is just to do a L day A plus U. And then like L dow type equal to 2 is to use the Dudarev approach, because there are like different like approach to use. I mean, I always use the Dudarev, and the Dudarev is the more common. Okay, so this is true, this is 2. Okay, and then L dow is for the quantum number for which one-side interaction is added. Okay, if you have -1, no one-side interaction. And why you have 2 and -1? because remember that you have 2 nickel and 2 oxygen. So for the 2 nickel, you want to apply the Dudarev correction on the quantum number 2, and the quantum number 2, remember, that is the one that is related to d orbital. So these two here means that you want to apply Dudarev correction on the d orbital on the nickel, of all the nickel atoms, okay? Then you move to the second element. The second element is the 2 oxygen, and here you put -1. What does it mean to have -1? To have this -1 means that no on-site interaction is provided. So it is telling, but don't apply any correction on this element. And remember that you always need to put -1. I mean, in this case, you could not have put just 2 and it's okay. Because in the postcard and in the podcast, you're giving 2 elements, nickel and oxygen. So you need to tell VASP if he needs to apply any correction on the second elements or not. If you can try to remove this number, run the simulation will fail. Because VASP will be like, okay, but why you give me 2 elements and then you don't tell me if you want the correction or not on the second element. So nickel, correction 2, because you want to correct on the d orbital, oxygen -1 because you don't want to apply any correction, and then here with this L dou G, you are including the U value and the J value. So you will tune this value, as I said, when you don't know. So you will have 1, 2, 3, 4.5, 6, whatever you like. This one, L dou G, usually is constant to 1. Now they put 0.95 to be fancy, but usually you keep it to 1, and everybody does it. And you see that you have 8 and 0.95. So that means that for the 2 nickel, you have a U bar correction of U equal to 8 and J equal to 0.95. And for the oxygen, you have a U correction of 0 and a J correction of 0, because for the oxygen, you are not applying any U bar correction. And yeah.
So sorry, for the nickel we are putting 2 because we are referring to quantum number 2, which is about the D electrons, and we need, for example, on the oxygen they are not necessary.
Exactly. Okay. For the oxygen, because the oxygen doesn't have D and F orbital, so you don't have this problem. And in case, for instance, you were using an element that has the F, like the last simulation I ran, and a cation with the neodymium, and neodymium has the F orbital, then I needed to have L dou equal to 3. Okay? And that's all. And then this L dou print is just to print the occupation matrices in outcard. But this is something that you do in order to check after that your output on the outcard in a proper way. Okay? And so if you do this simulation, yeah, you can then check the on-site occupancies in the outcard. So again, more space outcard, you open the outcard and then you put slash occupancies, enter, and that will look for the occupancies pattern in the outcard, so you can see all the occupancies thing. And this is basically like telling you where you have, yeah, this is split by the different like well, not orbitals, but the, yeah, I think you got it. Like, you know, now I don't remember the proper term to define it, but you know, like that each orbital has different like yeah, I mean, no, I don't even, because here it doesn't even hybridize, but it's simply that, like, yeah, depending on the quantum moment, then you can get different like configuration of the orbital. So in the case of the D, you can have like the D on the XY space, XZ, like, let's see if I can just look at it. Now internet is a bit so the orbital. Okay. Ah, now it's faster. Okay, atomic orbital. Let's see. Types of this orbital. Yeah, okay. Yeah. So what I meant, these are just types of orbitals. Yeah. So, and this is what I meant. So you see that, yeah, for instance, like depending on the system, you can have different like distribution of the electronic density around the radius, and this is defined by these different like parameters. So the different parameters that you see here are the different like ways that your like electron density in the d orbitals can be like distributed around the nucleus. Okay, but not that important. And yeah, and then you can compare if you want like this value with the previous. So this is the correct one with the U bar. This is the one without the U bar. But the most important part is this one, because now you will see that you get a band gap around 3 electron volts. That is the right band gap. Okay. So the only take-home message that you need to take from this last simulation is just that for some systems, oxides mainly, or systems that have a D or F orbitals, since these orbitals are very, very, very localized, then you may need to apply the Dirac correction. So the U equal to something, J equal to 1. Okay?
And here's the Fermi energy 0.
No, I mean here the Fermi, like this is not corrected, I think, like Python for VASP, so the Fermi energy here is 0. I mean like, no, wait, because the Fermi energy for, so the point is that the Fermi energy is something that you define for a metal. So a Fermi energy is not properly defined for a semiconductor or an insulator. Usually the way you define the Fermi energy is right in between the band gaps. So the Fermi energy will be here. But again, like talking about the Fermi energy for semiconductor insulator is problematic. Okay, so even if VAS will give you a number, you need to be careful because Fermi energy is a concept that is developed for metals. Good, and then
So in the real project, if you want to use the plus U, I mean here, I mean, will be so complicated.
Yeah. So yeah, the problem with U is that whenever you use U is a mess. It's a big mess. You need to do a lot of benchmark. There will be a reviewer that will complain about you using the U because it's a formalism that is not well established. And it's also like any correction, it's just an additional correction that is not defined. So let's say like, I mean, it will be better not to use the U, but the problem is that you must use the U because as we say, like, otherwise you get even less physical meaning. Okay? What is the only important point, and usually what we did in the group whenever we needed to use the U, is just that you follow the state of the art. So if somebody else used the U on the system, you also need to use the U. Because otherwise you will be the only, or you have really strong evidences against using the U. But if you don't have strong evidence, then you need to follow the state of the art because you cannot be the only one in the field that wake up one morning and say, no, I don't use the U because I don't believe in the U. Because if all the other people use it, then then it's a problem and you need to use it as well. In the group where we needed to use the U, like for instance in my project about the copper oxide, what we did is to calculate the same system with U and without U and show that some parameters were independent. Because if you manage to show that with the U or without the U, the result is the same, then you are done because people cannot say, look, but why use the U? Maybe it doesn't work. Maybe without the U it works. You say, look, it works the same for both the things. But you always need also to include a calculation with the U because it's something that still like if you don't use the U is a mistake because as we say, like we have the self-interaction error. But also if you use the U, since the correction is also, you are not improving, let's say, like you're just correcting these mistakes, but you are having other mistakes. The only important point that is written in this very last slide, that you should never, never, never compare energies with different U. So what it makes no sense is, for instance, if you want to calculate absorption energy of CO on a system, and you calculate absorption energy of CO, and you calculate nickel oxide, for instance, MCO, with a U of 5, and then the clean surface, so just nickel oxide with a U of 3. That doesn't make any sense. Because the important part is that if you apply a U, you need to apply the U to all the systems. If you don't apply the U, then you need not to apply the U for any of the systems. And then you can do comparison between the two classes that you have. So no U and yes U, but you cannot compare yes U and no U, because the two energies will be different, because one has a correction and the other one does not have. Okay? But don't worry, because I mean, like, let's say, I think in the group, if we had, I don't know, 40 projects to run, 2 or 3 of them have the U. So it's not really something like, okay, 50% of probability you will get a calculation with the U. So don't worry about it. Good. So it's 11:45. I think this was the last slide, yes? So if you want to discuss about anything, we still have like 15 minutes. Also, Mariam, if you have any question on any point. Right there. Because I always need to play with this before. Wait a second.
Because microphone is
No. Her microphone, well, now it's closed, but yeah. Her microphone, well, now it's closed, but yeah. Okay, yeah, now.
Yeah, no, it was okay for me. Thank you. I need to go through them to understand more, because when I'm going through them, I understand how much problem I face.
Yeah, no, that is normal, and I think it's general for everyone, also for Santiago, Enrique, and like the theory of today is very heavy in general. What is important, and also tomorrow that we will go through the answer, is just that you get the concept. I mean, that is the most important point. Like why you need to apply a U, what the U is giving you, and all these kind of things. I mean, then, like, it's not that important that you get to understand the formalism between the U, like behind the U, because at the end, like, you will not be the one. You will not be the one working probably on improving the U formalism. So you just need to apply the formalism. So as far as I understood how to use it, you are done. Okay. So nothing more to. Okay. Good. Yeah, and just to remember all of you, I mean, now I close this. That yeah, we have the last 2 classes basically, and then you can all start with maybe I can start sharing again quickly, just to go again. So at the end of the 4th class, as always, I also added like a bunch of suggestions for the comment. Okay, so like what you can do, like you can go through them, and that should help you to copy the hands-on input from my Tekla home folder, to enter, check the incar, prepare the run script, submit the run script, and check like with the VASP run, like the output that you want. So if you forgot any of the command, then you can just go here and like check the command that you need to run, and nothing else. And then remember that this week we will just have like Tuesday, so tomorrow we have for 1 hour like the tutorial, and on Wednesday we have correction, and then we are off. You wanted to say something, Mariam? Yeah.
Yeah, Federico, when I'm going to VASP, I still, my page is completely blank. So I don't know what's the problem of it. Should I say any simulation or other thing, or should I choose something in VASP?
Okay, so like when you do that, you are doing tunnel 1 and tunnel 2, right?
Yes.
Okay.
In tunnel 1, they asked me for the password, but in tunnel 2, they don't ask for the password.
That's strange. Okay, that's because usually they should ask. Okay, and then
so they should ask for both, yeah? In both tunnels, they should ask for my password.
Asking both, exactly.
Okay.
But then,
okay.
I mean, maybe that I don't remember properly. Yeah? Then after that, you enter Tekla home, right? So let's say in the same like terminal where you apply tunnel 2, you apply this command, so you enter Tekla home, right?
No, I open another the third terminal to enter the
You can
file.
also open a third terminal, perfect, and then you enter.
Yes.
Okay, then if you enter Tecla Home, you can see folder inside, or no?
Okay.
Yes or no? Can you see the folder inside or not? Okay, but
Yes, actually, I can go.
you can. Okay, wait. I can quickly.
Yes, please. Thank you.
I can quickly go to what I mean. Okay, so I mean I have something a bit different because I don't have these two tunnels, but the commands are the same. Okay, I just call them tunnel 1 and tunnel 2. So you see here that my Tecla Home is empty. It's empty because I don't establish any tunnel now. So what you need to do in one terminal, this one is okay, tunnel 1, and here is asking me one password. Now you keep this terminal open. You don't need to close it. This one needs to be open because it's opening the gate for you to enter in the other field. Then you open a new terminal. I will still put it here just to make it bigger, and then I move it on the left. Then on this terminal, I write tunnel 2. Yeah, it's asking me a password, so I should ask you a password. Remember that in your case, you need to put tunnel 2 space your username. And if it doesn't work, then we can, during the day, when you have a second, we can check the command together, because maybe it's the command that is wrong in the virtual machine. It may also be. Then in this case, after that, if I enter the say Tecla Home, so you see here, Tecla Home, I try to type ls and nothing happened. If I do it now, then now, since I have this tunnel open, I can access all the Tecla Home folder in my own computer. So now, if I enter like one of the folder, like for instance, I can enter Anson, I can enter the solution of the Anson of today. And for instance, I go to C43 nickel. Now, I am inside the folder, I do Python for VASP, and now I'm able here to open Python for VASP, okay? And here, for instance, like for Wednesday, you can check the density of state, okay? So if you go to those, now you see that we have this beautiful bandgap that is the bandgap that we want to have, because we have this, like, yeah, you see that here is, well, actually, yeah, what I told before, like that usually should be in the middle. Python for VASP doesn't care, so they put the Fermi energy to 0. You see that they put the Fermi energy like to the highest occupied band, but it doesn't matter. The important point is that here you have this band gap of, yeah, more than 3. That is the one that should find. Okay, but this was just like a small like things about the exercise. So but instead to come back to the procedure, Mariam. So tunnel 1. Open and they ask for a password. Tunnel open, you open a new terminal, keeping the first one open. Tunnel 2, they ask for a second password, you enter Tecla Home. You should see all the folder in Tecla Home. So in case you try to enter Tecla Home, you type ls and you don't see anything, that means that the tunnel command is not working, because you should see all the folder that you have here in the supercomputer, okay? And then after that, you enter like the 00 VASP course, you enter one of the folder that you want to check, like 4,3 nickel oxide, and you check the password, for instance. Clear?
Okay, sure. Thank you.
Just try, and in case like you try exactly the same process and it doesn't work, then send me an email, because there is a problem with the script, okay? It's not your problem.
Okay, thank you.
Good. So, any more points to discuss here? Oh, then I can stop sharing. And as we said, we see each other tomorrow for 1 hour, and then on Wednesday for 1 hour. And yeah, like if whenever of the 2 days you need to discuss or ask things about the Python script, we ask. Okay. Then by the end, and if by Wednesday we manage to get the solution, we are all happy. And if we don't have the solution of all the script, doesn't matter. Okay, in the sense that like it's not that like you will be evaluated. But of course, if you have the solution, then later on during your own project, when you will need to do the script, you already have the script done. I mean, otherwise you will need to finish the script later on for your own project. I mean, it doesn't matter for me, it doesn't change much. Okay.
Okay.
Then we are all done, no? Good. Then bye, Mariam.
Bye.
Thank you very much. Bye.
See you.
Bye,
Well,
guys.
bye.